All right. Okay. So there are two addresses. One is LBA is just like the virtual address in the OS, and PBA is just like the physical address in the OS. But actually, these two addresses, there is no relation between like operating systems. I mean, those addresses are dedicated inside the SSD, so there is no relationship between the operating system and FTO design. Okay. So when we are going to update this LBF 500, actually what we are going to do is we'll find a new block in we'll find a new patch in other blocks. So like this, if there is a new patch in block 2, then we will read out the patch from block 1, and then we'll modify those bits that we are going to update to. So in this example, we'll update to the red bits here. And then we'll write into a new patch in block 2, for example. So at the same time, we will update the patch mapping relation. In this example, like we move the PBA from PBA 800 to PBA 1201. Then actually they are using the same LBA because the virtual address, I mean the logical block address doesn't change. The thing that changes is the physical block address. Okay, so we change the physical block address and left the LBA becomes the same. And in this scenario, actually, user applications or user programmers, they do not really know what happens inside the SSD because all these kind of remodified write, they are finished by the SSD controllers. So the CPU inside the SSD. So the next time, if a user is going to read out like LBA 500, then SSD controller will help to do the remapping and to find out actually LBA 500 is now remapped to the PBA 1201. Then the data stored on PBA 1201 can be read out. Okay, so this is how the remodified write be implemented inside the SSD. And this patch remapping or like address remapping is quite important because with using a patch address remapping, users do not really need to know what happens inside the SSD. Okay. So actually, we also point out there are some limited lifetime issues for SSD because each NAND flash cells there have their own lifetime, and the lifetime is because the capability for capturing the electron inside the floating gate, there is some limited there. For example, if one day like it is not possible to capture the electrons inside floating gate, then the NAND flash cells becomes worn out. So wheel leveling is also performed inside the SSD, but actually we do not really talk too much about this perspective because like I think this is a little bit advanced topic. So yeah, the thing you need to know is SSD will help to cells so to make all the NAND flash cells can endure very similar amount of the writes. Okay. So the second things that we need to talk a little bit more about is the how CPU access the peripherals. So we say there are two different ways for CPU to access the peripheral. First one is the port mapped I/O. So port mapped I/O CPU use a special instruction. In this example, we give the in and out instruction to access the I/O address. So for the memory address, generally CPU use the low store instructions. So you can find like if we are going to use a port mapped I/O, we need another instruction set. Okay, so this will be another overhead there. And memory mapped I/O, I think you guys are more familiar with because memory mapped I/O is just to let I/O address to be mapped on the memory address space. So for the 32-bit systems, the memory address space, virtually there are kind of 32 bits, right? So we just reserve some of the bits on the 32 bits for the I/O address. So the good thing is actually CPU can use a low store instruction to access I/O address or memory address because they share the same address space. And the thing is, we don't really need another instruction set here. Okay, but But the things for the port mapping I/O is like this. If in like several decades ago, because we don't have that much of the address space. For example, in the 32-bit system, we can only address up to 4 GB, right? 2 to the 32 is 4 GB of the address space. So now if there's a lot of I/O device and they're going to share the 32-bit address space with the like memory device, in this case, we don't have that much of the space for using the memory mapping I/O. So several decades ago, people are using these port mapping I/O solutions to solve these issues. But now, I mean, now like in the recent like 10 to 20 years, actually we are moving from 32-bit system to 64-bit systems, and we have 64 bits of the address space for memory. So actually, we have a lot of luxury to use the I/O address. Okay, I'll come back for DMA later because I have another new slides for the port mapping I/O and memory mapping I/O. So here are a little bit more details about how MMIO and PMIO for. So MMIO maps device register and buffers directly into the main memory address space. So remember when we are talking about SSD, actually inside SSD there are also like DRAM buffer, those kind of things. And also for some device, there's register inside to control the device. So when the CPU is going to configure the device, CPU needs to access those register and buffer. And CPU can decide to use memory mapping I/O or port mapping I/O. Okay. So maybe you guys would be curious about why we need two different kind of I/O. I mean, actually, MMIO can do a really better job than port mapping I/O now, right? Because we have like 64 bits address space, so we don't really need port mapping I/O. But in terms of the compatibility, actually, early systems use PMIO for simplicity, and then we can save the like the memory address space here. But when we change to kind of powerful systems, if we don't want to kind of invent a new operating systems or like a new version of operating systems, then usually people or like usually the kernel developer will enable this capability. Compatibility. So actually, this is the reason why now there is still the support for port mapping I/O. But I mean, in most cases, current systems only use the memory mapping I/O. Okay. So here is also a table that I try to arrange about what's the difference between the port mapping I/O and memory mapping I/O. So I think there are some interesting thing I just marked it as a red. So in terms of the address space usage, as I mentioned, port mapping I/O, they have their own address space, not shared with the memory address space. So it can preserve a little bit of the memory space. I will just say a little bit because usually when we are using port mapping I/O, usually we only use like 16 bits or like 8 bits. So that this kind of consumption doesn't really matter a lot. But I mean, if you are using the 32-bit system, it really would be a case here. So for memory mapping I/O, just like I/O device and memory device, they share the same address space, so they do have some contentions with each other on the address space. And for the performance, usually, actually, when you are using port mapping I/O, there is some performance degrade here. The reason is you use two different kind of instruction set. So for CPU, then it needs to switch between these two instruction set. CPU cannot just use one like low stall to access memory and I/O. When CPU needs to switch between the instruction set, like when we're using the in-out instruction, then CPU needs to switch to in-out instruction. And when CPU is going to access the memory, CPU needs to switch back to a low stall. So CPU needs more time to decoding the instructions. Okay, so this is the reason why it takes a little bit more performance overhead for the port mapping I/O. And here's an example. I mean, for the same mouse and keyboard device, actually there are two different interfaces for mouse and keyboard, right? Currently, people are using USB-based mouse and keyboard. And for USB-based mouse and keyboard, they are all belonging to the memory mapping I/O category. But in ancient time, like there is PS2. So PS2-based mouse and keyboard, they're using a port mapped I/O. Okay, so they're the same device, but the different interface will make CPU needs to use different kind of protocol to support the I/O addressing. Okay, so there is about the port mapped I/O and like the memory mapped I/O stuff. And then let's move a little bit back to the DMA. So actually DMA is not really related to the using port mapped I/O or memory mapped I/O. Actually, DMA is another concept. So DMA, just like the figure shows here, DMA is we need another controller called DMA controller. And DMA controller can help to do the data transfer. So come to think about it, if there is no DMA controller, CPU needs to move the data by itself from the I/O device to the memory, right? So CPU will just store there or like synchronously wait here for the I/O completion. And it takes a lot of time because CPU cannot switch to other place. Okay, so DMA controller is here to solve this problem. So if we can have a controller, it doesn't really need to be so powerful in CPU. It can be a very like embedded, like low power, like CPU there, and it only the role of that DMA controller only for data moving. Okay, so CPU will offload the kind of data movement job to DMA controller by doing some configuration. What kind of configuration? CPU will let the DMA controller know which data address in the I/O device should be moved to the memory address. So for example, if we are going to move the 4 kilobyte data from I/O device to memory, then CPU will tell the DMA controller to say, hey, let's start to move the data from a certain I/O address. And then the size or the offset is how much, like 4 kilobyte. Then DMA controller, after getting these instructions, DMA controller will start to move the data like from I/O device to the memory. Okay, so after CPU like offloading this instruction to the DMA controller, CPU can do other things than just moving the data. CPU can do running other process like this. So DMA controller, you can think about it just like a delegations for CPU to move the data. And there is a question from you guys is about, then it sounds like DMA is a great solution for data moving, right? Because introduce this new hardware like controller, it can greatly alleviate the CPU overhead for data moving. It is true, but there are also some constraints for DMA. So actually DMA, because it is a very primitive or like it is a very like simple controller here. So usually DMA controller usually support to move the data in a continuous way. So there are several things that DMA controller will work not that efficient. For example, if we're going to move the small data, for example, if the data is like several bytes there, then because each time CPU needs to send the request to the DMA controller to move the data. So if CPU frequently send the request to the DMA controller, it takes time. So in that case, CPU can just move it by itself if the data is not that much. Okay. So there's another scenario is about the non-continuous data. So for each time, DMA controller can only move the continuous data. Because as I mentioned, CPU will only send the DMA controller the starting address and how much we are going to move. So if the moving is not continuous, then CPU needs to send a lot of DMA requests to the DMA controller. So it will take a little bit overhead here. But actually, in most systems now, we use the DMA for most of the cases, okay? Because like CPU's resource is quite important for the process and for most of the cases. So using more DMA controller is also a good trade-off here. Okay. So actually last time we didn't really give you some example about the device driver. So last time I just mentioned about actually in Linux kernel, there are 70% of the Linux kernels, they're all device drivers. So I just bring out the Linux kernel 2.6, and then there is someone do some arrangement about, hey, actually for there are some for character device, block device, and network device drivers, and all these they are belonging to the device driver. So like 70% of the kernel code, they are all from device driver. Just some one things to let you guys know. So okay, here is the things I'm going to add a little bit more for the device driver part. So come to think about if now we have a device, it is about the USB to Ethernet conversion device. I think this is you usually use this kind of device if you don't have enough like Ethernet socket, right? You will insert the USB to Ethernet conversion, this kind of device into your notebook, for example, and then your notebook can support the Ethernet. Okay, but how does this device work? So usually, like Linux or not Linux, like most of the networking, they follow the TCP/IP stack if you are going to send a TCP/IP request, right? So Linux also support this kind of TCP/IP protocol layer. So the thing is, when we are going to send this packet to the USB to Ethernet controller device, and there are usually two. I mean, there will be more, but I just make it simple. There are two here. One is USB to Ethernet driver, and the other is USB bus driver. Okay, so USB to Ethernet driver, there's some protocol that we need to follow for Ethernet family protocol, right? So if we are using TCP/IP, then there is some TCP/IP protocol. So the kernel code will encapsulate this kind of protocol inside the request, and then send into the USB to Ethernet driver. And then we have another encapsulate is because this device is connected with the PC or like with the notebook with the USB interface. So we need to encapsulate another layer is the USB driver layer. Otherwise, the packet cannot be sent into this through this kind of device. So we have USB driver to support these kind of things. Okay, so if you still remember, we mentioned about like actually device driver is going to communicate with the controller on the device, and then usually like we say there's a PCIe controller, there's a USB controller. Usually they are on the motherboard. Okay, because the motherboard like is the place you plug in your device. Okay, on the motherboard, there are several sockets there. There are USB socket, there are PCI socket, those kind of socket, they are all on the motherboard. So those kind of controller, USB controller, PCI controller, they are also on the motherboard. So to drive this controller can communicate with those kind of device, we need some kind of software, and that kind of software is the device driver. So you can think about after kernel encapsulate those kind of drivers and then start to move, actually this kind of packet will be first sent to the like USB controller on the motherboard, and USB controller will decapsulate or like resolve this kind of package and then send the USB to Ethernet driver to this inside this device. So the device can read out the protocol, can follow the protocol, and then to resolve this USB to Ethernet drivers information there. Okay, so then we will finish one like transmission from the device driver to the device itself, and this is how it works. And so like I think there's also a question is about how PCIe driver works, how NVMe driver works, and usually they are very similar. PCI driver is going to configure the PCI controller. Okay, so they also use this kind of driver kind of idea to implement it. Okay, so that is for that. So last time we spent a little bit more time talking about the buffer and the buffer heads, and also the block I/O. So I will quickly go through this kind of idea, and then jump into the file system part. So there are several keywords here. First of all, is a sector. So sector is the smallest addressable unit for a storage device in the system perspective. So no matter which kind of device, from the perspective of the block layer, actually they are using this kind of sector. So there are 512 bytes here. So you're using hard disk drive or SSD, it doesn't really matter because this is about the point of view from the block layer. It is not the controller inside the device. Okay, so here is a sector, and then when we say block, it's about the smallest addressable unit of the file system. So the relationship between the sector, block, and patch will be look like this. Like patch is larger than, I would say like no smaller than a block, and a block will be no smaller than the sector. But they can be the same size. For example, the block and sector, usually they can be the same size. Okay, so the thing is about like when we use the file system to allocate this kind of block, it is about the data on the store device, right? Because file system is going to manage the data layout on the store device. But when we are going to read out the data from the device, it must be read into the memory before being accessed. So there is the concept called buffer. When we move this kind of data from store device to the memory device, it is called a buffer. Cool. Okay, and because this kind of buffer in the memory, we need some ways to manage it. So for each buffer. Okay, so for the buffer head, there are several kind of information in here to describe the data. So here are about like what's the status of the data in the store device, and then where is the location of the data in the store device, all this kind of stuff. Okay, but we say like actually buffer heads, there are several issues here. So the first one is about it is large and bulky data structure, because each buffer head contains all this kind of information, and even more. Actually, I only drop part of it. Okay. Okay. But a block is smaller than a patch, right? Because we see a block is only 512 bytes, but a patch is 4 kilobytes. So it means like if we are going to maintain the size with the same size of the patch, for example, we need like 4 kilobytes for the patch, then we need 8 blocks to put in one patch, right? Because 512 byte times add is 4 kilobytes. So in this case, we need 8 times more this kind of buffer head to describe only one patch. Okay, so it spends a little bit more kind of space overhead to store this kind of buffer head data structures. So the first solution to solve challenge one is to directly work with the patch, not with the block for kernel. Okay. And the second one is about kernel should break up large block IO operation into multiple buffer head. And the reason is because we say each buffer head can only represent 512 bytes. Okay, so all these kind of challenges, they can be solved by the BIO structure. And BIO structure, it manages the block device not from the sector size. It is from the operations. What do I mean for operations? You can think about one structure BIO is one block request. So inside the request, there are several operations here. And what we define for operation is it should be aligned with the segment. So a segment means a chunk of the buffer that is continuous in memory. Okay, and it doesn't really need to be in what kind of size. I mean, it doesn't really need to be in 512 byte or like in what kind of size. So the reason is like this. For each BIO dash vector, you can think about for each I operations, we can control the data on the patch. Okay, so the segment, they can be larger than patch, or even it can be smaller than the patch size. Okay, so like this. The question will be like how to position or find the position of the segment. So for example, if the segment is in any place on this patch frame, so we need to record several things. The first one is which patch it is, and the second one is where is the offset, and the third one is what is the size of this segment. Okay, so for using these 3 parameters, we make the segment become so flexible. What do I mean? With these 3 parameters, the BIO structure can find out which patch frame store this segment. And then inside the patch frame, there are like 4 kilobyte, right? But maybe the segment size is smaller than 4 kilobyte, and it is not start from the very beginning. And if the segment starts from like this address, then we need an offset to position where is the starting point for the segment. So the offset is like this. Where is the starting point for the segment inside this patch frame? And the third one is how large it is. So we use this kind of length parameter to record about how large the segment is. Okay, so with these three parameters, we can easily identify each segment. Okay, so for the block IO request, it's submitted from the file system. For example, we will read out several kind of segments. Like we will read for the first segment for using this BIO dash vector, and then for the second BIO dash vector, maybe we are reading from another segment, or even we write to that segment. So we can combine several segment operations together with using only one BIO structure to describe it. Yeah, this is how like BIO structure differs from the buffer head. It is more flexible and it doesn't really need to consume that much of the address. Sorry, not that much of the storage capacity for memory, and also for using the BIO structures, it integrate with the patch structures. Okay, so this is about the BIO things. Last time we start at the BIO structure, so let's start from the following after the BIO structures. Actually, inside the Linux IO management, like in the block IO layer, there's a thing called request queue. So the request queue is going to store pending block IO requests. So you can think about it's about from the file systems, it submits a lot of BIO structures because there are several users there. So different users, maybe they submit one or two. So there will be a ton of block IO structures. So for the block IO structure, they will be stored in the request queue. Okay, so if we simply sending out requests to the block device in the order that the kernel issue them, then we don't really can enjoy the like locality on the data assets on the, for example, hard disk drive, because we say for hard disk drive, using the sequential access would be a lot of better than using the random access, right? Because hard disk drive, it uses the plate to rotate, and if we are accessing in the sequential order, then we can get a lot of performance benefit. But on the other hand, if we access the data randomly, then we cannot. So the thing is about, if we already know there are a lot of requests here, and each request there are several segments there. So is it possible to do some scheduling, just like how to minimize these six? Maybe we can merge and sort the pending requests in a queue, right? Because with this kind of request queue, I mean, there are several segments and maybe they are in the neighbor, then we can merge them together. But maybe they are from different block IO requests. So it is possible to merge different block IO requests and then to sort them to make it sequential. So hard disk drive can access those kind of, can finish all these kind of requests in a better format. So there's another idea called IO scheduler. It's going to solve this problem. I mean, it is possible to schedule this kind of block IO requests. And it decides the order of the request in the queue and at what time each request is dispatched to the block device. Okay, so there are several ways, just like it can coalescing two or more requests into one. And then we can sort the requests in a sector wise. I mean, the starting point of the sector, we can sort them. So after the sorting, we can minimize the disk seek and the rotation delay there. Okay. So this is about the overview about the IO scheduler, but I think we don't have time, so I didn't really put too much of the details about how to do the IO scheduler here. I mean, if you are interested in, we can have more kind of description for like the next like semester. We have another course talking about this kind of stuff. So okay, let's move on to lecture 5, file system and virtual file systems. So now we learn from the device, like we already learned about the hard disk drive and solid state drives, and also we learned about the device driver part and then the block IO layer part. So actually, until block IO layer, the design is still in the point of view of the how to make a good management for this storage device. So those are not designed for making user easy to access what kind of data. So file system, the goal for the file system is going to let the user can access the device or can access the data more intuitive. User doesn't really need to know what is block, what is sectors, and what is like store device. Users only need to know file. And file is a virtual concept because before before file system in block IO layer and block device driver, we don't really name file there, right? There's no files in the block IO layers and block device driver. Okay, so from the disk perspective or the SSD perspective, there's no file concept here. Okay, so there are three main topics for a file system. The first one is file system itself. Just like there are different kind of file system, ext4, XFS, logback file system, those kind of stuff. And then there is patch cache. And then there are virtual file systems. So patch cache is more about if you are going to read out the data from a storage device. And maybe in the very recent times, you are going to reuse or like to access it again. Then we need a way to put those file data on the DRAM so we can reuse it. So this is the concept called patch cache. And then there's an idea called virtual file system. So virtual file system is more like actually in our system now, it can support using different kind of file system. For example, you can have your first disk using the ext4, the second disk using XFS, and the third disk maybe using like exFAT. So they are all using different file systems. Then in the programmer perspective, is it possible to access those different kind of file systems in only one like program, I would say like program paradigm. So it means like we only send the read request to each kind of file system, and each file system can work as it is. And this is how virtual file system works like. Just like all of the users, they only work with the virtual file system. And virtual file system will help to communicate with different file systems. So programmer doesn't really need to know, maybe I'm going to talk with the ext4, so I need to use ext4 instructions. And I'm going to talk with the exFAT, I'm going to use exFAT instructions. No, there's a little bit too complex. So this is about the virtual file system. But I think today we only talk about the file system part. So file system is a method and data structure that the operating system used to control how data is stored and retrieved. So without a file system, data will be one large body on storage media, and it is hard to separate and identify for the user because there are a lot of like segments, a lot of sectors there. So users doesn't really know maybe which sectors means what kind of data. Okay. And Linux supports many file systems here. So generally, there are two different perspectives for the file system. One is disk-based file system. So for disk-based, about to storing files on non-volatile block-oriented media. So there are exe family, XFS, exFAT, or even like Mac OS file system. They're all about the disk-based file system. Okay. And there is another very famous is called network file system. Okay. So network file system is the file might be on a different system carried out over network connections. So we need to know where is the file is. Okay. So maybe I think this is a little bit too abstract. So it is not really easy for you guys to understand. So I try to make one like example. Like if we analog the IO system to the library. So library users just like the applications. And if there are library users, they are requesting some books, for example, it means like application is going to get some files on our systems, right? So file system is just like the catalog systems. Catalog systems means like, for example, I'm going to find a book. So I know the title of the book. I know the authors of the book, and I know when the book is issued, for example. So those kind of information, they will be stored in these catalog systems. And then we can use this kind of information to find where the book is, right? We can use the author's name, we can use a title, we can use a date to do the filtering and then to get the books by using these catalog systems. Okay, so same as file systems. So we have a lot of files and they have different file names. And then they have their users only in these kind of files. So to get the file, to locate the file, we need this kind of file systems. But noting that actually the catalog system is just letting the library users or library staff know where the book is. We don't really get the book from the catalog system. It's just going to navigate the staff and users to know where the data is. So the library staff basically, oh, sorry, there's a typo here, retrieves the book from the correct shelf and slot, and they are analoging to the block layer and the device drivers. So the library staff just like a block layer, because the library staff, after checking the catalog systems, it knows maybe it is on which shelves and which slots. So the library staff will go to get a book. And this is how block layer is. Block layer getting the information from the file system. As we mentioned, the file system will send a BIO structure to the block layer. So after getting the BIO, the block layer can locate about, okay, where is the data is, in which kind of disk, and the block layer will send to the device driver. So device driver here is just more like the way to get the data. Okay, and device is more like the correct shelf and slot. So device, you can just think about there's a lot of bookshelves. It is called device. Okay, so this is an analog between the IO systems and library. So once again, file system is just like the catalog systems. So it is, I would say, like it is a virtual layer between the users and the device. So device actually doesn't really know what is the file, and users, it only knows the file. Users don't know where is the data is, or like what is the location of the data, those kind of stuff. Okay, so this is for the file systems example. Okay, so let's talk about more kind of details about what is file system in the Linux perspective. So file is just like a linear array of bytes that can be read or written by the systems, because we are using the binary systems here. Okay, so actually each file inside in Linux system, it has a lower level name. It calls the inode number. So it uniquely identifies itself in the file systems. The reason is because for Linux system, it supports a lot of users to use the same systems at the same time, right? So different users, maybe they have the same file name file. But maybe, for example, they using the same file name, but the content is not the same. So we cannot directly use a file name as our identifier. For example, there are two users, and they just write, for example, txt for the file name. But for different users, txt, they may store different content. So if we directly use a file name as our identifier, then we cannot really uniquely identify the file content. So for Linux, actually, file name is not that important, because in the perspective of the Linux file systems, they only identify by the inode number. So each file has their unique inode number. Okay, but I mean, users doesn't really know what the inode number is. Okay, and I will show you how to do the conversion later. So in Linux, there's the second one. Special thing is about a directory is just a special type of file. So directory, when you are using like Windows and Mac, maybe it looks super different from the files, because the folder and file, there's two different concepts. But in Linux, actually, directory it is just a file. There's no difference between directory and file. Okay. So because each directory is just like a file, so each directory has an inode number as well. Okay. So you can think about a directory just like a directory file. Okay. So the third one is about Linux. Now they're using the directory tree to help to navigate where the data is. So the directory tree looks like this kind of stuff. So it always starts from the root. So the topmost node here, the backslash, means the root directory. And after the root directory, for each node here, we use a separator, and we use the backslash as a separator. Okay. So a file referred by the absolute path is from the root. So this is the definition for an absolute path. So like the path should always include the root directory. Okay. So in Linux, there's absolute path names, or like there is the referring path name there. Okay. So directories and files can have the same name. Just as I mentioned, actually, the name is not really important for the Linux. So directory are just like the files, and they can have the same name, but they will have different inode number. Okay. So when you are using Linux, you can have the like folder name and the files, they'll be the same. Okay. Okay, so you already know for Linux, there's no difference between files and directories. And also Linux doesn't care about the file extensions. So no matter you're using .pdf, .pptx, or like .txt, for Linux, it doesn't really care about what is the file extension it is. Okay. So let us dive a little bit more about the technical part. So when we the reason is about, like I said, no care is about the way to open the file is about there is a way, like there is application, there is a way to log about how to open this kind of file. For example, there is a link with the inode for that file. No, actually it's about like each file they have their own inode. And then for the inode structure, they will record about what kind of applications we can open this file. Okay. So actually the name is not really important. I mean, even you change the name, for example, in Linux, you change your name to from .pdf to like .pptx. But if you said about the default opening is using the PDF reader, you can still use the PDF reader to open it. So it is not about the link between the file name and how to open the application. Usually it is about, it depends, but I think it is about like link the inode and the how to open that applications. Yeah. So, okay. So let's integrate a little bit more about the process and the file. So there is a concept called file descriptor. So file descriptor is an integer to identify the open file in all file-related operations. And you can think about when you write a program and then you say you program you write a things called fread to open a file, and at the same time you will get a file number, a file descriptor there, and more like this kind of stuff, like this. So for different process, like if you are going to open a file, for example, this is the first file, and you will get one file descriptor called 1 or 3 or like 4. Okay, so usually the first few file descriptors, they are reserved for some important usage. For example, debugging usage, for example, the error handling, those kind of stuff, or like the read and the write, those kind of stuff. Okay, so but you can think about if you are going to open a file, then you will get like FD like 20 or like 19 or 18, this kind of stuff. Okay, and different process, they can have the same file descriptor because the concept for file descriptor, they're only inside the process. So different process, the file descriptors can be the same. Okay, so the file descriptor is assigned by the kernel when a file is open, and it's valid only within a process. Okay. So for the inode is another concept. Inode is about each file has just one inode, contains metadata such as access right, date, pointers to the file data. So inode actually it doesn't really only be a number. It is a data structure, and inside the data structure there's a field called inode number, and there's also more things than inode number there. There's access right, that pointers to the file data. Okay. So here's an example. If you have two processes and then you have the process open different amount of files there, and usually inside Linux there is a conversion table called open file table. So this open file table is going to link with the file descriptor with the inode number. Okay, so inode number, because like for a system, maybe you have a lot of disks. So different disks, you are going to store the data on it. Okay, so each data on a disk should has their own identifier, and this is called inode. So inode need another data structure to maintain it. Okay, but from the process perspective, for example, FD1, okay, maybe here, FD2 and FD2 in process A and process B, maybe they can point to the same inode. For example, this 73 here, they will be directly linked to the inode number 5139. So that means like process A and process B, even they're opening the data from different process, but they're opening the same file data here. Okay, so it is about like it makes the process has more flexible to identify each kind of file data. It's just like file descriptor you can think about just like a file name managed by the process. Okay, and how to link the file name to the file content itself is about there is an open file table and an inode table to help to link with where the data really stored on the storage device. Okay, and inode table or inode structure means where is the location and what is the data stored on the storage device. Okay, so this is about some technical stuff for the file systems. Okay, so maybe we can take a 10 and come back later.
你们有就是这个 struct BIO 它是一个 request，
对，
然后这个 BINext 是会去指向下一个 struct BIO。
我想一下哦。对，我这边好像写错。
所以这样是不是应该是指向下一个 request？
对，我这写错，应该是next request。
OK，
没错，
那这样就没问题了。
对，我再改一下。
好，谢谢。
是一块大的，
就是这一块跟这一块其实是
不会有上下区别，应该是就是
对，没有上下区别，它是直接写下去的，
是连在一起，然后只是它这样画表示要 read 的时候就是读半，对，的大小就是读半条，
没错，
就是这条来这样，
没错。
我想问一下，就是它这个 storage device 这边不是有一个 sector， 对，它是先放到这个 block， 然后再跑到 memory page。
我觉得他应该这样说，就是 block 它其实是做档案系统分配的大小，所以档案系统它可以分配跟 sector 一样大，也可以分配比 sector 还要大。所以它这个 block 讲的是 storage device 上面的状况。
哦，
对，只是说因为它这个地方是就是因为我这边写的是这里是 smallest addressable unit of the file systems。对，那档案系统通常是管那个硬碟上面或者是就是储存装置上面的状况。对。但是我们要存取的时候需要拿到记忆体，所以才会出现这个拿去是一个 buffer 的状况。
哦，所以这个就等于只是一个空间，让它放 storage device 上的东西嘛。
就是可以这样想，因为它 block 比较像是说，你有一个档案，但你的档案可能比 sector 还要来大。
对啊，
它可能有2个 sectors。那对于档案系统来讲，它一个 block 可能就是2个 sector 把它框起来，然后代表这是一个 file。
哦，
对。然后这对你一般使用者来讲，这就是第一个档案，或者就是举例来说好了。对。那我要存取这个档案的时候，这2个 sector 会直接被它搬到 buffer 里面去。
哦，
就搬到 memory 里面去变成 buffer。对。但是呢，这里的话，我们就是把它说的是把 block 搬到 memory 里面去变成 buffer。对。它比较像这种感觉。
好，应该是了解。然后还有一个我看一下哦，就是这个一个，
我都写错了，不好意思，这个是 next request 才对。
哦，对，我那时候在想，所以
我等一下跟大家讲一下。对，
因为我那时候在想是 one block IO request 就等于 one block IO operation。
没有不，
所以
其实我觉得这边很 subtle， 我觉得这边其实每个人讲都不太一样，但是我后来的总理解就是直接分成 request 跟 IO operation 分开会比较好理解。就是一个 request 里面它可以有很多 IO operations。那 request 这种东西它其实是从档案系统下来的，所以它可能可以是我要读很多个区域的资料这样子。 对，但它都是集合在一个 request 里面
所以一个 request 可以有很多 operation，
但这里的 operation 定义就是它需要存取连续的区域，因为它一个 segment 是连续。
哦，
对，
所以它这边这一个框框指的是一个 IO request，
就是
这个，
对，
然后包含
就是这个资料结构是在
IO operation 这样。
对对对对对。
哦，好，好，然后还有，再看一下，就是这个 churn 是可以再讲一下。
哦，这意思就是说，今天因为我们说它 request 可以发很多出来，可是你每个 request 每个使用者要读的档案，通常会在不同位置上面。但如果我们照它的顺序读的话，我们就很有可能就是今天第一个使用者跟第二个使用者，它相对来说，它假设我第一个使用者好了，我顺序的位置是在这个点之后，那第二个使用者在这个点之前。
对，
可我 disk 是这样旋转的，所以如果我先执行，不好意思。这是第二个使用者，然后这是第一使用者，但我这样旋转了。但如果我是先做第一个使用者，做第二个使用者的话，那我就等那个disk转到这边之后，我才办法做。
哦，对啊，
对。但是如果我今天它都把它放在一个 Q 里面了，我其实可以去对这个 Q 去做排程之后，其实我就可以先做第二个，再做第一个。
哦，是这个意思。
对，
好，然后这个叫，这个就是这 catalog 的意思，就是它只是记录那本书的位置。
对，就是那个图书管理系统这种感觉。
哦，然后它就要告诉这个 library staff，他那本书在哪，
在什么地方，
他才可以去找。
对，
好，然后看一下哦，就是我想问一下，就是 file name 是一样的，它不是在系统里面，就是我们自己平常在存文件的时候，它不是不能有同样的文件名吗？还是只要在不同的？
那个是因为系统给的限制，就是 Windows 给的限制，或者是 DNS 给的限制，但它跟 file system 通常不一定会有直接关系。所以它有可能是可以的，只是为了避免管理上的麻烦，就是这里的管理上麻烦是 Windows 在设计这些使用者界面的时候，为了避免管理上的麻烦，所以要设置这个限制。对，但是这里的话，通常都是以 Linux 来讲。那 Linux 来讲的话，基本上你可以用你可以用同一个名字哦，但是它最后在答案里面是会有不同的，就是对应的
哦。
对
哦，好，然后我想问一下，所以你说它这个 file extension 是什么意思？
就是点 PDF 点 .doc 这种。
好，然后还有最后一个问题，就是我在想问，你不是说每个 file 可以一定要有不同的 inode number 吗？
对。
那它这里为什么可以指到相同的 inode table？
那代表是同一个 content，就是它是同一个档案。
哦，
在储存装置上，它可能就是一个就是电影档，但是你不同使用者可能在不同时间点会开它。
哦，
那不同使用者开它的时候，它会有不同的 file descriptor。对，因为不同使用者他可能宣告很多 file，但他可能宣告顺序不一样，所以他们拿到 file ID 是不同的，所以他们最后都会连到同一个档案，就是那个电影档。
哦，
对。
哦，就是比如说这个 process A，它开了很多 file，就会有很多 FD，
对啊，它就很多 FD，
然后每个 FD 又连到不同的 open file table，然后他们因为如果最后开同个档案，就会连到这个 inode。
对。
谢谢。
就是来自于这每一个 track 的那个人跟配置是什么？就是具体想象还是台湾还是水我要怎么写？
他就是看这一块磁铁怎么去感应这个 track。
所以我也可以就是 SN 这样，然后可是 read 的方向都是固定同一个方向去 read， 然后看感应的磁场会是
没错。
就是求那个提加分是有需要登记还是？
有，就是第一堂课有讲，就是要把问问题直接就是寄信给学校。对，就是。
我想问这个比较，就是它不是需要额外的资金吧？为什么它比较复杂？
有这个吗？因为它这个是 I/O 跟 memory 都共用同一个就是定值空间，所以我们需要一些额外的处理去处理，就是一些额外。对。那这个是因为它硬体上面就把它分开来了，所以它硬体上面本来就有2个不同的字音字，所以它就不太需要去管理这个，就是 I/O 到底在哪个范围，然后 memory 在哪个范围的问题。
那这个现在是没有在用的吗？
我觉得，不能说没有在用，只是说用的很少。就是一般大家的一般电脑是比较不会用这个，但是例如嵌入式系统或者它的记忆体， 需求比较有限，就是它的定值模式用的比较有限的话，它就会去。
不要去占它的信息的话，
对，
就会这种。
没错，对，
这样
好，谢谢。
这个意思是，就是 iKnow 那边嘛的时候，本身就会去考量这些里面的内容，然后去做编辑。
哦，不是，其实是因为我就应该这样讲，因为我刚才没有讲很好，就是 iKnow 其实是一个字头结构，然后它的字头结构里面含有非常多的栏位，然后 iKnow 的就是 ID 只是其中一个栏位，然后这栏位里面还有这么多其他的，就是它
是有很多属性的意思。
对，没错，
了解。谢谢。
是。
想问一下，因为刚刚没有听清，就是想问一下，就是这个 open file table 的就是用意是为什么？
就举个
就知道那个 ID。
举个例子，就是说，如果今天我有2个使用者，然后我2个使用者都想开同一个电影的档案，然后这个同一个电影档案呢，它都存在同一块就是硬碟里面的，就反正就是同一个档案的意思。那同一个档案的话，对 iKnow 来讲，它就是有一个固定的，就是那个 iKnow number。可是对我们的 process 来讲，i 哪个档案就是你开第一个档案就得到第一个 ID，然后第二个档案就得到第二个 ID。但是 process A 跟 process B 它可能是开到那个电影档案的时候的顺序是不同的。就 process A 已经开了第10个，然后那个第11个才是电影档案 ，process B 可能一开始就开那个电影档案，所以那个电影档案在 process B 其实是 FD0，然后 process A 可能是 FD11。那我们需要有一个办法去把它，就是去做对应关系，知道说这个，所以这个 open file table 就是做这个对应关系。
你是不是那个 iKnow？
就是这个 FD 假设我们这边对 process A 来讲，我开到第11个档案，我才开到那个电影。然后对这个 process B 来讲，我可能第一个档案开起来就是开那个电影的。但这样它的 FD 这边是 FD0的，不是 FD11，那他们就会全部都指到同一个就是 open file table 这个地方。那他就知道说，哦，其实这2个 FD 讲的是同一个电影档案。
那为什么他不能这边说他直接知道这 ID，就比如说他正标之前还是这2个直接知道他对这个？
啊，你是说为什么不从这边
就是说为什么需要经过这个 open file table？因为我们不直接知道那个 ID。
我记得，这个我等下再回答你，但是我记得原因好像是因为他这边如果直接指过去的话，它会有一些管理上面的复杂度。
但没有那个 status，就他
对，但是具体来讲，我可以下礼拜再跟你说。
好，谢谢。
好。
现在 source name pending 是要不然 version starting of pending request 是什么意思啊？
就是你今天如果送了很多 IO request 到系统里面去，就是假设你现在有1000个使用者，1000个使用者都在差不多时间发 request 进来，那你这1000个 request 的话，它可能就会被放在一个 queue 里面。那你就可以有机会去做 merge。对，
就是先不是所有人都发现直接处理它，
对，不是，就它有一个 buffer 时间可以让你做处理。
像刚刚这个图上面有个那个 USB 那个 PCIe 那个是什么？就是 PCIe 那个是
就像 USB 那样子，
就是那个，我以为把它是什么？就是 PCIe 嘛，
就是
对啊，是 data 要从进去或出来，
就是你的接口，就是你今天它这个是 USB device，所以是 USB 接口。那你如果是 PCIe，
这个地方，
对，
这里我没有，
那也就是说，如果你今天有个 device 是长这样子的，然后它的功用是把它 USB 讯号转成就是网络的讯号，因为这是网络的接口。那你今天要做2件事情，一件事情是你需要去把你要给的讯号包装成是这个转换可以看得懂的，所以这是底层。
说那这说，
就是我就要把一个讯号传到网络传出去好了。
你说network 吗？
对，或者资料从网络传出去，
然后转给系统看得懂。
我要先转给这个 device 可以看得懂的。对，所以我先封装一层下来。就我像封包一样，我先封装一层下来。但是这件事情呢，只有这个装置上面的 controller 可以看得懂，这怎么去解它？所以首先你需要先把你的地那上面的资料先透过这个 USB 转接头转进去，然后你的系统上面有一个叫 USB controller 在你的主机板上面，然后就透过这个 USB bus 的 driver 这个就是它上面这一块，就是它这边上面有一块晶片。
他这个工作，你有朝你说他工作是这样，
没有，就是这里的 control 指的是它要去转 USB 的讯号，把它转成图讯号。可是你从系统里面传资料的时候，你会需要把系统转到 USB 去。
所以这是目标，是不是？目标
对，目标是
network 到 USB 还是？
没有，就是这个装置是它帮助我们的。假设我们现在的笔记电脑没有，
因为我想说为什么会有2层？
因为你要先第一层是要让这个装置知道你的讯号要怎么把它转成 USB 转成网络。第二层是你要把这个资料从你的电脑丢到这个 device 上面的，要怎么丢？
然后意思是说，这个意思是说，然后所以这个 USB bus driver 意思是说 computer 到这个网卡，
对，
到这个 driver
对。
USB 到 network，然后第2层是 computer 到这
对啊，这你要
片东西。
对，
这是网络卡。
对，算是网络卡。
OK。
好，谢。
确认一下就是那个 file system 在file system 在操作的时候，它是对那个virtual file system 是对 file system 做抽象，
对，做抽象，
对，就不管下面什么都可以。然后 file system 它不会对 device 的 address，它不会对档案实际上在 device 的哪里知道，它只会对一个 logical 的 address 做操作。然后所以它的 inode 里面就会存可能档案在 logical address 里面的位置，然后它的一些 metadata 之类的。
对。
然后它今天要开启某个档案的时候，它就是把这个包含 logical address 的东西发给 block IO layer，然后它知道这个东西要怎么转正下面 device 的实项的位置。
没错，
好，
没错。
至少自动的变异是，它为什么它都会以前懂的关系。所以说是为了你这个话它是会比的。这是一个，因为我是两个来说，有的，说啊，我觉得我们需要一些证明，而且他们也是因此没有自由的，应该有受回讲，也在你是外的在手外的时候，而且都是长期的，所以会看到我一样的。啊，你那个其实刚开始少了，那个时候就很正常。
All right, so let's come back to, let's push our progress a little bit more, and then I'll let TA to take over for introducing our third hands-on. And before that, let me clarify one thing. I think here's a typo in this slide. Actually, this one should be the next request, because this one, bi.next is about to point to the next BIO. So it should be point to the next request. Okay, so and this bi-io-vector, this pointer will point to the bio-vector. And bio-vector means one operations. Okay, and one operation means to access the continuous data in the systems, just like in the patch. Okay, so here is a request, not the IO. Sorry, not the IO operations. Okay. So there are also some concepts for like soft links and hard links. I think it's quite interesting, so I just put it here. So soft link is just like the shortcut, just like no matter in your Windows or Linux, actually there is a shortcut concept. And soft link is about a separate file contains a path or reference to the target file. So this is only about the reference, not really get the new file. So you can think about like this. So this is our indexing for the files. So like the file.txt. And if we are going to create a shortcut or a soft link for this file.txt. So it will like this. This is a soft link for this file. And actually, because this is a shortcut, so this is also another file. So it will get another inode number here. But the thing is about actually the inode number will point to a very spatial data block. They will point back to here. Okay. So actually this file.txt, this reference can help to reference back to file.txt. And then we'll go through the same path. The file.txt will find the inode number, and inode number will point to the data blocks on the store device. Okay, so this is the reason why when you double click on the shortcut, actually you can still access the original data because the shortcut will redirect back to the original data. Okay, and then if you delete this shortcut, actually the original file will not be deleted, right? But if you delete the original file, then the shortcut will be missing. I mean, it cannot link back. So this is the reason here. And in addition to soft link, there's another concept called hard links. So hard links means the file shares all the attributes of the original file. Because in soft link, actually, we only create a dummy file or like a reference file. So it doesn't really point to the data blocks or like the real data. And for hard links, it is about they share the same inode. So no matter the original file or the hard link files, they share the same inode. So they can point to the data blocks. Okay, so the reason for using this kind of hard links is about sometimes when you are going to back up the data, and in this case, you can use a hard links to back up the data. Otherwise, if you use a soft link, it is not really a backup because using a soft link, if you misdelete the original file, then the reference or like the soft link cannot get back to the original data. But using a hard link, actually, how many hard links with the original file you will have a counter to keep track of these kind of numbers. For example, if you have one original file and one hard link, then the counter will be 2. So if you misdeleted the original file or delete the hard link, the data blocks will not be deleted because the counter will just drop from like 2 to 1. And the counter goes to 0 will trigger the delete operation here. Okay. So this is about like soft link and hard link. And in Linux, actually, you can try on your Linux to use this kind of soft link and hard link command line to try it. Okay. So, oh, this is not recall, sorry. So this is the layout concept of the file systems. And then I think this is quite interesting for you guys to know. And this is also very important. So file system, just like it is going to describe the data stored on the store device. Okay, so we use an example is if this is a store device and the physical layout of the file system on the disk is like, one moment. Okay, before talking about this, let's first give you some assumption. If there is a directory tree like this, there is one subdirectory 0, and then under the subdirectory 0, there is file 1 and file 2. And another directory is subdirectory 1, there is file 3. And then we have one file is in the same directory with the subdirectory 0 and directory 1. So as we mentioned, let's first move on to look at this inode part. So for the inode part, actually, for each directory and each file, they have their own inode. So you can see that each one they have their own inode. Okay, and the difference is about if this is a file or if this is a directory. So if this is a directory, then we will get the directory entry. And for the file, there is no, the shared directory entry. So what do I mean? Like this. If we're going to store this kind of structure on the store device, first of all, in the store device, in the very beginning of store device, there are 2 blocks. One is called boot blocks and another is called super blocks. So boot blocks is when we are going to boot your system, then system will read out CPU will read out the operating system from the boot block to boot your systems. Okay. And then a super block is about, because for each disk, you can have your own file systems. So this super block is going to describe which kind of file system you are using and what kind of rules you are going to follow. So superblock is just like for this disk, maybe you are going to partition to, for example, ext3, for example. Then this superblock is ext3 superblock. Okay. But also in this storage device, actually, it is possible to partition into two disk partition, and then you give different file systems. Okay, so on the same disk, it is also possible to have more file system on the one disk. Okay, this is just a kind of interesting to let you know. And after the super blocks, actually there are a lot of slots. You can think about just like the inode table. So this inode table is going to point to the data block or the directory block. Okay, so after the inode table, there is an area called root directory. So the root directory start here, and then, for example, file one's content they will be stored in data block. So there are two kind of data blocks. One is for file data, and the other is for the directory data block. Okay, so for file data, just like the content for file one will be stored in this data block. Okay, so when you are going to access the file, the data belonging to file one, you need to first check the inode table and then to find where is the data block, and then the file inode table will return you, okay, file one is stored on which kind of location, and you can start to read out like file one, for example. Okay, but how about this subdirectory 0? Because this is a directory, and we say actually directory in Linux it looks the same as the file. So actually it looks like this. Oh, I think this is not important. Let's skip it, come back later for this one. Okay, so actually for directory, it is also the data block will become a directory block. Okay, so inside the directory block, there are several directory entries inside, because this one is subdirectory 0. So inside subdirectory 0, there are two files, right? So for these directory blocks, we maintain the directory entries correlated to this directory. So for example, because we store these two files, then for the directory entries, there will be two entries. The first one is to let us know what is the inode number for the first file. So because file one here, the inode for file one here is 4. And then the inode for file two here will be 5. So in this example, inside the directory entries, the first directory entry will go for inode 4, and it also maintains what is the file name for this file. Okay, and also for inode 5, it is belonging to file 2, and it also will store the file name for this inode. Okay, so one interesting thing to let you know is actually the file name is not stored inside the inode. In Linux, the file name is stored inside the directory entries. Okay, and the reason is because the inode here they have the same size, but because file name usually you can have different name for the file name, right? So if we store the file name inside the inode, then the inode table will be hard to maintain because there will be variable size for the inode table. Okay, so in Linux, their decision is to move the file name into the directory entries. Okay, so this is about the data blocks and directory blocks. And I think there is actually this figure is, I just get this figure on the internet, and there is some error here, because here they said for this one, for this subdirectory 0 here, they're saying like, hey, actually this is the D entry 0, but actually this is not the D entry 0. It is the directory. Okay, and what is the entry we will introduce next time, because the entry will be related to the virtual file system structure. Okay, so I think maybe we can first go for the third assignments, and then if we have sometimes we can move on to the following content. Okay.看一下哦。哦，知道。你们叫听不懂？
我开那个网页。
那我可以贴给你。
我自己按那个，
好，
还不是这样。
哦，你要这样哦，好，可以。
哦，打错了，
打错吗？等一下我把它拿回来好了，这样比较好看。
可以，我可以拉回来在这里，然后
可以可以可以，我来帮你拿过去。
没有这我。
没关系，
啊，
不用。
好，这个可以拉回去。
那我拿过去。还是你要不要开镜像？我觉得镜像可能比较好，
镜像。
这样就不用看那边。电脑，我把这关掉。叫关掉。
有，
这样，啊我把这个拿掉。
这边还好，要放旁边或拿掉。
哦，没关系，反正这边应该不重要。
啊，
这样
可以，好，可以这样。
行啊。
Okay, so today we're gonna give you guys the assignment 3. So if you use some Linux tools, you can go and find a tool called NeoFetch, or there are other similar tools to do this thing. And these kind of tools, you can see that it will give you like the system information, like which version of the operating system it is, and what kind of hardware you are using, like the CPU, GPU, and how much memory you are using. And for this assignment, we will want you guys to make a simple version of that, which is this one, this photo here. And this assignment, mainly you will need to write a Linux kernel module. And this kernel module, you will have to, kernel modules are a dynamic piece of code that you can compile yourself. And given the kernel version, you can dynamically push this kernel module, install it onto the current running kernel. And you can add functionalities to the kernel as you want. And so if you want, you can use lsmod to first look at what kind of kernel modules that your system is currently loaded with. Yeah, I'm just gonna do this. So this is a standard machine. So if you type lsmod, you'll see a lot of modules that are installed, like sound core, maybe it's going for sound or something, and other things. And so you can also use another tool called mod info and the module that you want to look at. It will tell you some information about what kind of module this is. Given the TLS module, it will say like, oh, it's written by Mellanox Technologies and what its subversion is. And so to write these kind of things, we have provided a small guide here on the internet. And on here, they'll tell you more about the kernel modules, and it will give you some simple modules like how you write a simple module and how you compile it. And so the target of this homework is that you will have to list out the kernel release, the kind of CPU this system is using, the number of CPUs it has, and memory and number of processes and its uptime. And so you should, after you load the module into the kernel, it should be named a kfh module, which is here, kfh mod. And so we will provide a user program to read out information from the kernel module, which here, it should have a bit mask, and it will ask the user to give out some arguments to it. Here, I will demonstrate it. Oh no. So we will give you kfh.c and kfh.h to let you guys compile your code for the user side of the program. And the user side should communicate with your kernel module to get some information. So this kernel module that you will be writing is also characterized. So there are some, some default operations that you will have. So usually you will at least have to implement open release, which is when you load the module and when you unload the module, and then read and write, because we will have you guys to give the arguments to this module via writing operation, and reading because you want to read some information from the system. So these are some skeleton codes that you would try to use and reference to. And so the requirements is that you will have to use this given logo to the readout, because at your readout you should see this picture, and on the left side that is a little ASCII art, so you have to give out this part also. And then other things is that you should write your code like properly. You shouldn't be like, if you load your model and unload your module, the system will crash or something. And so yeah, to test your own code, you can compile the code we have given you, and you give them some arguments, and it will change how you would use how the information is displayed. So, oh, and also another thing is that what you need to give us is your own makefile. Like the second assignment, you have to give out your own makefile to compile your kernel module and your C code. And if you have other codes that were needed to include to compile your module, you can also include it. And here I'll demonstrate like how it should work. So first, you'll want to compile your code, right? You just use make command. And so this is like it's compiling the code. And so after it is compiled, you should also write a load target so that we can just use make load to load your module into the kernel. So now I have given the command make load to load the module into the kernel. So if I use lsmod, there should be a kfetch module here. There is a new kfetch module that I wrote and now is loaded into the kernel. And so to interact with it, you can just use our given code to our given user program to interact with it. But one thing is that you have to use sudo to let it have the permissions to interact with your device. Sudo here. So after you just give the kfetch program, if you run it at default settings, it will list out all of the kernels, CPUs, and stuff. Also, you can use some arguments listed here, some options to only show part of the information. So if I only use -c-m, it should only give out CPU and memory. So here, it will only list out CPU and memory. And one thing to be considerate about is that after you run your, you change the settings a little bit, you will have some partial of the full information, right? The next time you run it, it should remember your settings. So like at the last time that I run it, I didn't give it any command, any arguments, right? So it should do what it did last time that it read the kernel, reading the module. So it should mean that it is using -c-m. So if I change it again to only -m and run it without the argument, it should only print out mem. Yeah, and that is mostly it. And for the grading part, you should absolutely make sure that your code can be built under any directory. If your code doesn't compile, like it doesn't compile if we change the directory and it fails, you will very likely get a 0 score because it shouldn't be dependent on where you put your directory that your code couldn't compile. So here you should give like some reference or some command to resolve the path to the compiling part of it. If you want to know more, you can read up the programming part of it. And another thing is that there are some public test cases that you should know, like if you print your host name and kernel, you get some points to it. And there is some private test case is that if we have multiple processes that will read your device, it shouldn't just crash. And it shouldn't give something weird. So yeah, that is pretty much all of the things that this assignment is asking. So is there any problem that you guys want to ask or any clarifications? Yes, it is the finals. If for the extension part, we will discuss it a little bit. We will try to see if there is some time after that. So this part, if there is an extension, we will give you guys a notice. Yeah. And is there any other questions about this assignment? Also, currently the assignment should be up in E3, so if you want to read it up, you can read it up right now. Yeah. So is there any other, questions you want to ask or anything about it? Sure. Then that's about it.
All right. So because we have some time, so let's come back to talk a little bit more about the log structure file system. All right. So we introduce a layout for how to put the data on the store device and how file system layout these files or like the data. And the next question is about, so on the list layout, how to find an inode? I mean, given a request, how to get the inode from this kind of device? So let me give you, I think it's a long example based on a log structure file system where we're going to talk about how to get the inode based on this file system. Because for each of the file system, they have their design concepts, so maybe different. But I'll just based on this log structure file system to give you some insights about how this kind of management works like. So first of all, we still need to come back to our challenge on the hard disk drive, because actually the data like file system is invented. Also, people are using the hard disk drive. So this is the reason why most of the designs they are related to the hard disk drive. Okay, so at that time, hard disk drive, it should follow the disk rotation, this kind of access pattern. So it should be, I mean, if we are going to get the better performance from accessing hard disk drive, the sequential access is quite important. So actually, there is a subtle difference when we are talking about the sequential access. The scenario is like this. If we are going to write data in a sequential order on the hard disk drive, even it is a sequential order, but this is not enough. Okay, so the reason is about actually the plate on the hard disk drive rotates all the time when we power on the hard disk drive, right? So when we are saying like we are going to write the data on a sequential order, for example, I'm going to write like 3 files and in the sequential order, file 1, file 2, and file 3. But we didn't mention about the time like we really write data inside, right? For example, if you write the first data and then you pause for like 5 minutes and you write a second data, and then you wait for another like 10 minutes and you write a third data. And you cannot make sure these 3 files, they are very close to each other on the plate because the plate moves over times, right? So we cannot control where is the precise locations for these data to be very close to each other on the hard disk drive. So this is the reason why the log structure file system comes. Because a better way is, or like I'm not going to say the better, I mean, one of the possible way is to issue a large number of contiguous writes. That means like this. That means we need to maintain a write buffer. So write buffer usually just like you need to partition part of the DRAM for this kind of write buffer. So we first will buffer this kind of updates in the DRAM, and then we'll write in a batch to the hard disk drive at the same time. So with this manner, we can make sure this data, they can be continuous on the hard disk drive. So like this. If here are several kind of data here, like DJ0 to DJ3, okay? So DJ0 to DJ3, actually, they are all belonging to the same data called DJ, but it is so large, so there are 4 parts here, okay? So in this example, you can see for DJ is a file. So we give it an inode called inode j, right? And for inode j, there are 4 blocks belonging to this inode, block 0 to block 3. So block 0 means to give it some physical location here, okay? But the case is like this. Okay, one moment. Okay. So the case is like this. If we are going to write the data at the same time to the hard disk drive, we can make sure they are all in a sequential order, right? But if you if we consider another case, we first write DJ0 and then write DJ1, DJ2, and DJ3 one by one. But because one by one, we cannot make sure, for example, when this write buffer is going to write DJ0, DJ1, maybe DJ2, and maybe at the same time there's another process. It is also writing the different data on the disk. And at the same time, maybe there will be interleaved with other process. For example, DJ0, after writing DJ0, maybe there's another data called DI from other process. Then DI0 will write near to DJ0. In this case, the data cannot be continuous on the hard disk drive. So having the data together in the write buffer and then write them at the same time to the hard disk drive is very important for the concept for the log structured file systems. And the root cause is because the disk plate rotates all the time. And also there are several processes that are working at the same time. So we cannot make sure if we write the data one by one to the systems, we cannot make sure they will be placed together, even they're in the sequential writing order. Okay. All right. So, okay. So when we write this kind of data structure on the hard disk drive, actually we say this is the reason why, if you still remember in the layout slides here, actually the boot block, super block, and inode table, actually they are all stored on the device. They are all stored on the storage device. And the reason is when one day you shut down your computers, actually those kind of files and information, they are all still maintained inside the device. So if one day you power on the system again, then you are going to reconstruct the file system back. We can just read out the data from the disk. Then we can reconstruct this kind of file system out. Okay, so same here. We write this kind of data and inode together into the hard disk drive, right? So in this case, we always need to find the inode before accessing the data because we don't know where is the data block until we can find an inode. Okay, and inode is just like a data structure, so there are several information inside. So the block location is one of the information. So for example, for inode J here, they comprise 4 blocks location here. They are from A0, A1, A2, and A3. A0, A1, and A2, and A3, and they are on the storage device. Okay. So actually, for another data means DK, because this is another file, so we have give it another inode code, so-called inode K. Okay. But here comes a question. I mean, how to find an inode in the disk? So for old Unix file systems, a very simple way is to organize in an array and place on disk at fixed location, right? If we have a fixed location for inode, then we can always start from a certain location and we can find it. Okay. So like this is an old Unix file system, for example, and here is the data, like D1, and then to a lot of data here, and then different data that placed in the hard disk drive, and then we will reserve maybe, for example, the last amount of the space they are placed in the inode. So this is the first inode. Second inode means first inode will manage the first file. Second inode will manage the second files. So inode always store at a non-fixed locations, right? In this case, when we are going to access the inode, it is quite simple. For example, because inode is in the same size, so we only need to know the starting point for this inode structure. You can think about this inode table. It starts from A stars. So having this A start, we can directly get any inode in this area because they are in the same structure. So it's just like an array. So given an index with this starting point, you can always find the inode. So this is the simple way. Just like we just give it a set of amount. So for example, if we are going to get this kind of A inode, and it means like A star plus the inode index times the inode size, then we can get it. Okay, so this is one important thing is here. The inode size is a fixed size, right? The reason like we can do it like this is because the inode size is a fixed size. So this is the reason that I mentioned in last class is we will not put file name in the inode structure because file name sometimes can be super large. It depends. I mean, you can make your inode file name super large, and the size will be hard to control. So in order to make the inode size to be in the same size, the file name was put in the dirty entry, not in the inode. Okay. Okay, but here comes a problem. Let's come back to the prior slides. Okay, if now the scenario is like this, if now we are going to take the benefit of the sequential access behavior of the hard disk drive, we should put the inode close to the data, right? Getting the inode, then we can get the data. So if we can put them on a very close tracks on the hard disk drive, then for example, the rotation count, then the disk head can read out the inode and the data at the same time. Then we can directly present the data to the user. That'll be super fast, right? So this is the reason in this slides we say moving them together from the write buffer to the hard disk drive is a good solution. But when we come back to the old Unix file system, the problem is they separate out the inode and the data, right? Because they are going to calculate where is the position of the inode, so they cannot mix the data and inode together. So it means at least we need two assets to get the data. First, we need to first get the inode, and definitely inode will not be in the close location with the data, right? Because data is super huge, and inode, if you have a lot of files, the inode table will be super large also. So you need to first get the inode first, and then get the data later. So you need to at least two disk access, right, to get the data out. Okay. So consider this scenario. If we are using this kind of log structure file systems, like here, actually we put the inode close to the data, or even we say we make the data and the inode they're stored contiguously. So in this scenario, after reading the inode DJ3, DJ2, DJ1, DJ0, they can be read out at the same time. So we only need get the disk head at this position, and because the disk will rotate all the time, so we can easily read out all the information we need to parse this file. We only need one disk access, then we can parse the data. Okay, so if it is possible to mix the inode and data together and then put the inode close to the data, then we can save at least half of the time, right? Because this one, we need 2 times of the latency, and this, we only need half of the performance to get the data. But the reason is, if in this case, then how to know where is the inode? Because inode and data, they are mixed together. Okay. So there is a way it's called the checkpoint region. So checkpoint region is a fixed and non-region on a disk. It contains pointers to the latest piece of the inode map. Okay, so the concept is like this. Actually, we still need a physical location to help us to locate where is the inode. Come to think about it, when we are talking about the patch table walking, we still need to get the very first table, right? We need to put the first patch table address at the CR3 register to start the patch table lookup. The same thing, we need some place to guide us where is the first to get the inode. So here are 2 concepts here. The first one is about the checkpoint region, and the second one is the inode map. So we are saying like, hey, actually, it is hard to record each inode one by one. So how about let's group it together? So for example, for inode map, the first inode map means we manage from the 0 to the J inodes. We make it in a group. So each inode map will locate a group of the inodes, a group of files. Okay. And then for each checkpoint region, we are going to maintain a group of the inode map. So for example, this one, checkpoint region will only point to the inode map. And parsing the inode map, we can get an inode. Okay, so inode map usually will be continuous with those data maintained in this inode. Okay, so we use this kind of indirections. We get to, like, we amortize the code. For example, if the assets, the file assets, they are belonging to the same inode map, then we can get a benefit, right? We can get a benefit about, we can just read the checkpoint region and then read inode map. And because inode map groups like J files, so if the recent assets, they are related to these J files, then we can get a benefit here. Okay, so actually the time for accessing this, doc structure file system, the time will be between, sorry, one moment. Okay, the time will be between these two, because this is super slow and this is super fast. But for this one, we cannot find an inode easily. So a better way is to having an indirection. We group the inode together as an inode map. So in this example, if we use the inode map, then the latency might be between the slowest and the fastest. So this is the reason I say using this inode map, we can amortize it. Okay, but actually it's not enough. I mean, there is also a way for doing the optimization, but let's talk about it next time. So let's call it a day. Thank you, guys.真的吗？
就是这种就然后
哦，没问题啊，身体要均衡。
然后我有跟张老师跟你讲
哦，
最近会
他应该没差吧？对，但是这样子你的那个丹麦那个版，
就是因为你们不是就我到国外在
因为感觉到面如果要有的话，应该还蛮贵的。
你是一定是在哪？对，
好，
电脑上
好，没问题，反正对，反正你现在是非常超前的，所以我觉得没什么很大问题。对，
我那边都这样。
没问题，没问题。
就是关于我问这个 schedule， 它是它比较前面是比较高的 priority。
对，
那然后其实它是怎么去
你说在偶尔时间拿到吗？
判断说就是它有比较大的，
就是有比较大的，
老实说是看 bit 数，
就是它其实是 CPU 有一个指令是可以直接把这个 array 里面第一个有没有 set 的资料读出来，所以在这个里面，我其实用 CPU 直接我可以很快可以知道说是第二个位置有是代表目前是目前第二大的 priority 的 process。
这个有，可是它不是每个 bit 都会有的吧？
哦，这边说的有值是真的有 process 在等待
啊。
所以它每个 bit 都有是没错，但是它第一个 bit 像这个它是最高优先权的，它并没有 process 在现在在那边等。
哦，
对了，因为它这边没有开机，代表的是它没有 process 在这个地方等待被服务。那有 process 在等待被服务，我才把它 set 起来。对，
哦，
因为我固定我的一定会有140个 priority values。可是我不一定每个人每 value 都一定会有 process by 需要服务。对哦，对啊，因为我可能只来一个 process 啊，我那个 process 看在哪个地方。
哦，这边就是灰色地方是
真的有 process
哦，
在等资源的
哦，
对，
所以它白色地方就是空就是
对啊，反正这也不贵啊，140个 bit 而已。
哦，
对啊，
好，那就是因为老师之前说，就是如果是比它还要低的 priority，就是永远不会被支付。
哦，没有，这个是140个已经涵盖所有的 process，所有的优先权在 Linux 里面就是140个。 对，所以这边的话，基本上就是这边所谓的比它低不会被执行到是，它如果是 preemptive 的状况的话，那高优先权的人，他可能可以很快的被拿去做执行。
哦，
对，他就可以一直不断的 preempt 低优先权的。但是呢，这还是在140个优先权里面，只是说你可能很衰，就是你的优先权是第140，那你可能前面的人一直有人插进来啊，或者是一直有人做好了，啊，你永远没办法被
就是
记到。
你就要一直给这个。
对对，
好，谢谢。
好，现在
我问一下这个流程，所以他是先进来这边，然后再看在哪一张 map。
没错，然后在 map 里面再去找说它是哪个 INO。
那我这样算是读几次我的 base？
就是如果今天呢，它是那个连续的话，就是它这个 checkpoint region 通常啦，它会把这个 region 放在机体里面，通常
哦，所以这很快。
对，因为它很小，对，
嗯
然后它可以这样放，所以通常它是 IMAP 这样读起来是1块，
嗯，
但这个 IMAP 呢只能代表0到9个 INO，所以如果我刚刚好，接下来的都是在0到9里面的话，那我就读1次。它如果不刚好，或是在别的地方，那我就要读2次。所以它的 worst case 可以跟那个第一个是一样差，
这个，
对吧？
嗯，
worst case 就长这样，那 base case 就是长这样，
这个，
对，所以它是在中间的。
哪一个？
那它这个 I 到 J 这个大小是根据我前面的什么大小决定的吗？
哦，这应该是这下就会讲，对，它其实就是它这个地方应该没有做那么聪明，它应该就是固定好就是多少的
哦，
大小这样子，对。
了解，谢谢。
我这边没有，老师，我刚刚没听到，就是你可以再说一次，为什么这个是最快，跟这个是最慢？
因为你硬碟这样转嘛，那
对
你一定要先拿到 INO 才有办法做 data 的执行。
对，
那你这边的话，基本上你要先拿 INO，
嗯
那还是要 data 拿，
对
所以你要拿2次至少。
啊对
那你这边的话呢，因为你把 INO 放在 data 旁边了，然后
啊
因为 INO 通常比较小，
啊
那你要是直接这一块直接读出来的话，那这块直接读出来的话，它就只需要读1次而已。
哦，所以就是
因为这块很大，所以你不可能这边直接读，就是你不可能连续这样一直读过来，那这样你要读非常多资料出来。
哦
啊，只是因为这边刚好它就在它隔壁而已啊，所以你今天多读一个 INO 不影响那个运算的效率，但你可以就刚好利用到硬碟的特性。
哦，
对
所以就是因为这边比较小啊，这样比较大，所以比较小，它就可以刚好读到这个 I note。
对，因为这边它等于是把资料全部摆在一起，可是我们拿资料之前一定要先知道资料结构长什么样子，所以我们等于是要先读资料结构再读资料。那它现在只是刚好它读起来的时候是有包含到资料跟资料结构这两部分，
好，
然后它就一次可以做执行这样子。
那我如果今天这边很多笔资料，它就不能这样用了吗？
没有，可是它这是一个 file，就是它这是同一个 file，因为这些它都是同一个 file，
哦
所以它这边是一个 file 对一个 inode 的一个结构。
所以不管这个 file 有多大，
对
它都可以读。
对啊，因为它就是假设它知道是一 megabyte 好了，然后它就让齿头去读1 megabyte 之后出来。
哦，
但这个就没办法，因为它这个势必可能是什么好几 GB 这样子。
哦，原来
那你等于是你要花好几 GB，然后就只为了读到它的 inode，那就不划算。
哦，
对
然后啊，这个折中的方法是因为它
它这种方法就是它会把它 group 起来，就是这个 inode j 的话，等于是0到 j 都会把它放在这个 inode map 里面去。
对
但是这个也不大，因为它就是把就是一些 bit 一些 byte 而已。
啊
对，那它这个可以这样做，是因为它前面还会放一个 checkpoint region，可以去查说它到底在哪个地方，所以它等于是2段式。可是这个 checkpoint region 呢，因为它很小，因为它这个就是 summarize 几个 inode map 而已，所以这个地方会放在机体里面，所以这个存取不会是耗在 HDD 的时间，它等于就第一次被存取之后，它就把它放在机体，然后就再也不会被踢掉了。对，
哦，
然后接下来就看这边，那这边就是一个amortize 嘛，啊，如果你刚好你要读的人是这0到9个人的话，那你就赚到，你就跟最快的一样快。那如果你要读的呢都不在0到9里面，那你就是亏，那你就每次都要去别的地方读，那就是介于那2个中间。
哦，好，大概懂了，谢谢。
这样问题就是
嗯，
所以就是像他这样就可能是他有很多不同的 file，
对，
然后
所有的 file 全部都
他
放
会去那边，然后在就是以前是它是 A star 是放，就是可能固定从这个点开始，
对
然后 I know 往后，
对，
然后
等一下，我们换个场地，我出去一下，因为下楼层。